Man, today's gonna be a good fucking day. This shit is finally starting to make sense. Yeah. So that means that this shit is gonna start making sense for you guys too. Okay, so today we're gonna be talking about the architecture of a neural network. We're going to actually dive into the meat of AI and see like how it actually fucking works. It's gonna be cool. Like I'm really excited today about this one. So first we're gonna cover some linear algebra prerequisites because you need to know these in order to understand what's gonna come next. And then we'll walk through an actual example of a single layer feed-forward neural network, which is like the simplest you can get. Simplest neural network you can get, which is still pretty complex. Let's get started. First, linear algebra prerequisites. So what is linear algebra? Linear algebra is just a way of storing a bunch of data, basically. So where regular math like algebra and calculus deal with like all these cool functions that you can do and like what it looks like on a graph and all that cool shit, linear algebra is not so much about well, it's still about functions, but it's more about how do you store data, right? So how do you store numbers? So we walked through before, there's regular numbers, so scalars, one-dimensional numbers, two-dimensional numbers, matrices, three-dimensional numbers, tensors, and actually any higher dimension you still call tensor. Or you can call this a 0D tensor, or you can call this a 1D tensor. I think, yeah, 0D, 1D. Vector, sorry, I forgot vectors. 1D, 2D, 3D maybe. So the 3D tensor is just a regular tensor. And so let's actually walk through each of these and see what they mean. Scalar, vector, matrix, tensor. So first we got scalars, just regular numbers, any real number. Let's just, you can put imaginary numbers too, right? So imaginary numbers are not scalars. No, they are, but complex numbers. Okay, so let's ignore that. Regular numbers, real numbers. Okay, so this is 1. 1 is a scalar. Now what happens if I want to store two numbers? 1, 2. Guess what? This is my vector boy. Some equivalent notations are this. I don't know if there's any other ones. These are the main ones. I suppose you could also do like, you could define A as like your vector, and then you just call like A naught equal to 1, and then A1 equal to 2. Or you could say this is X and Y, or you could say this is I and J. Okay, I'm giving you guys too much random information. That doesn't matter. Here are the two ways you can store it. 1, 2, 1, 2. Why is this useful? Well, let's say we have like 2 dimensions, right? Well, then this vector grafts to this. It's like a different type of number. It's a 2-dimensional number. And so like this is useful, really useful in physics, but we don't care about physics. This is useful for AI, which is good enough. So yeah, vectors, cool. All right, interesting question. What if I want to express 3 dimensions, right? Simple. I just tack on another number to the back of it. I tack onto another scalar. And so now I have 3 dimensions, right? 1, 2, 3. Easy, right? That's the power of linear algebra. I can just keep extending this to as many dimensions that I need, right? So that's a vector. Next, let's talk about matrices. So matrices are just vectors stuck on top of each other. So if I had a vector 1, 2, 3, well, I can put another vector 4, 5, 6, 7, 8, 9. So matrices are just like these collections of vectors. And now tensors, even more fun, just collections of matrices, right? So you can see it's just ways of storing data. So like this, a 3-dimensional tensor, a 3 by 3 by 3 tensor would look like this. So to visualize this, imagine like me stacking a matrix on top of a matrix on top of a matrix. So it's like I have a 3D matrix, right? And once again, you can extend this definition. So you take a 3D matrix and then you stack it on top of each other into a 4th dimension. And now you got a 4D data tensor. Okay, never mind. Anyway, that's linear algebra. Now one last thing you gotta know, matrix multiplication. What is matrix multiplication? Well, we have regular multiplication, number is scalar multiplication. You can also call this tensor dot. Tensor dot or matrix multiplication, they're both equivalent. We have regular multiplication, 3 times 5, simple, 15, right? Take this number and then I add it 5 times, or I take 5 and then add it 3 times, 15. That's our definition of multiplication. But how in the world am I supposed to multiply something like 0, 1, 2, 3, 4, 5 times like, I don't know, 0, 1, 3? Well, these are not regular numbers. I can't just like take this and multiply. Like, we need to define some sort of operation, right? We need to define matrix multiplication. Actually, these two matrices can be multiplied. That's another thing. For regular numbers, you can multiply any two numbers you want, right? But these you can't. There's special rules. So let's say like, here's the rule. So if I have my first matrix row times column, my second matrix in order to be able to be multiplied by this must have the same. So like this number and this number must be the same. Let me show you an example. So like, let's say I have a 3 by 2 matrix. So 3 rows, 1, 2, 3, and then 2 columns. So we can say like 0, 1, 2, 3, 4, 5. And then I'm gonna multiply this, and my second matrix has to have 2 rows. So this can be any number you want, but it has to have 2 rows. 3, 4, so on and so forth, right? So this would be a 2 by 1 matrix if I just kept it here. And so my output, okay, so let's multiply these. How do you multiply them, right? Here's how you multiply them. Put this first matrix on the bottom left, and then put this matrix on the top. And so what you'll see is that this one should feed into the new matrix's first row, 0, 3. This second row should feed into the second row, and the third row should feed into the third row. And then from this one, the first column should feed into the first column. So that means it's kind of like you feed these in. 0 times 3 is 0. So here's the actual matrix multiplication. I'm going to take this number and multiply them, and then add it to this number. These two multiplied. So 0 times 3 is 0. 3 times 4 is 12. 0 plus 12 equals 12. So that's my final output. For the second one, I take the second row, and so now I have one column, I just go this way. So 3 plus 16, 19. And then finally 8 plus 20, 28. Pause the video and do some of these exercises so you can get really familiar with them. Try doing 5 by 6, right? See what that looks like. So what you would do is you would separate this, and then you would have a second column, and then you do this, right? Okay, and then finally, one last exercise. The output matrix, okay? The dimensions of the output matrix will always be the first one's row by the second one's column. Understand this, and understand it well, because it's very important. If you can figure out why this is, then I think you're ready to go on. If you're not, well, you can still watch, but it probably won't make much sense. And then you can actually extend this even further. So pause the video and figure that out if you haven't yet. And then you can actually go further. So we were talking about tensors before. Well, you can actually do the same thing. As long as these inner dimensions are the same, the output would be 3 by 3 and 4 by 5. So this would be a 4-dimensional tensor. Why this works, I don't even know. I don't think in 4D. But you know what? You don't need to. You can still probably figure it out. I just haven't taken the time to think about that yet. But it's still a rule. Okay, cool. Covered the prerequisites. Okay, let's talk about a neuron now. Because obviously if we're building neural networks, we need to start with the building block. We need to start with the Lego brick, which is neuron. So here's my little cute neuron. Okay. So this is a neuron. This is the mathematical version of the neuron, and then this is the graphical version. Both of these are equivalent. Both of these are a neuron. So this notation here, let me just do this. This denotes a vector. So this would, in other words, if you want to write it in the regular way, so like in the nonlinear algebra way, it would look like this. Both of these are equivalent. It just means that for every single one of these values, I'm going to multiply them with a weight and then add all those together. And what you'll notice is that this times a weight, this times a weight, this times a weight, it's exactly the same as matrix multiplication, what we were just talking about. If we have, like, let's say x1, x2, and x3, and I multiply that by 3 weights, w1, w2, w3, this is equivalent to saying w1x1 plus w2x2 plus w3x3, right? So that's why we use matrices in linear algebra, because they make our life easier. So this and this are the same thing. And then we add a bias vector. No, we add just a bias, not a vector. We add a scalar bias, sorry, my bad. Okay, so here's our neuron. What's our neuron doing? So, all right, our neuron has something called a pre-activation function. Okay, never mind. Our neuron has something called an activation function, and that's what this A denotes. What you'll notice is that once I multiply these two out, these two start as a vector, but they become a scalar, and this plus a scalar equals another scalar. And so this is just a regular function. A takes in some scalar. We can denote this as h of x. And it just outputs another scalar, which we call a in this example, right? So I'm just taking in some number and I'm gonna give you out some number. It's a simple function. Like this could be x squared, right? Like I could take in some value and then return to you like this value squared. It's simple enough, like this would look like this. Right? This is just like another variable. It's not too bad to think about. So that's our neuron. It takes in a vector, it applies some sort of function to it, and then it outputs another value. So let's talk about like why this is useful. So, okay, before, like in simpler machine learning models, I would literally just have one layer of neurons, or we could call it just like a linear transfer, or not, just a transformation, like some transformation of the input space, just one transformation, right? And then that would give me some useful representation of the data that I could then use to predict something about the original. Okay, ignore everything I just said. That was terrible. Ignore all of that, okay? Sorry if you were confused by that. That was my fault. Just fucking ignore all of that. Okay, back to this. Okay, so let's talk about why this is useful, right? Ignore all of that. So what I have here is, let me just make this bigger actually, is like how our model works, like from a very high level. It's just four things. It's just four things. Data, training data, our model, judging the output, updating the weights, and then just repeating this over and over and over again. And our model will get better and better. Each of these could take weeks to understand. So don't worry if this looks a little bit difficult, right? So what we'll do is over the next few days, we'll cover each of these in depth. We'll cover what training data should look like. So that's more of the gritty, practical stuff, linear algebra, and just what does the data look like? How can I manipulate it, right? And then we'll cover how you judge the output, which is our loss function. Then we'll talk about how you update your weights, which is our optimizer. This is where the gradient descent and the back propagation come in. But what we haven't talked about and what we're talking about today is the actual meat. What's the engine of it, right? What's the model? What is this black box? Today we're going to be unpacking this black box into something that's beautiful, something that's really cool. Yeah. Cool. All right, so let's zoom in on this model part specifically. So this is our neuron, right? If we connect enough neurons, we have a neural network. So let's create a single layer feed-forward neural network. Did I say single layer? Nah, that's too simple. We'll do a dual layer. Yeah, okay. This is gonna be a thumbnail. So what we start with is some data. So this is our x vector. Here are our two layers. Layer 1, layer 2, and here's our output. Okay, I know this looks like 3 layers, but this is just our data. Pretty cool stuff, right? Pretty cool stuff. This is our neural network. Isn't this cool? And like, some people like to show this data instead as being this. But I think that's a little misleading because all these lines represent scalars, like all these lines over here represent scalars. So it'd be a little unfair to assign these as vectors. So instead, I think this makes a prettier picture, but a more accurate picture is what we drew before. Although we can use a different color to denote that these aren't neurons and instead are just our training points. Okay, here is our neural network. Now let's talk about what's happening here. So if we zoom in on this one neuron, we can say this one neuron, all right, is this guy. Okay, so this one guy, now he's getting 4 data points. These constitute one sample. One sample equals one vector. One vector equals, in this case, 4 examples, or four inputs. So that's my x vector. x1, x2, x3, x4. These are just data points. 1, 2, 3, 4. They're just numbers. And what I'm going to do is my neuron is going to take every single one of those data points and then multiply them by some other number, and then add all of those together, which is what we were talking about earlier. This is where the actual knowledge of the neural network goes. Like, this is how the neural network gets better. Everything in the model is fixed except for these weights. The weights are what's getting updated, and the weights determine how accurate a model is, or network is. Now see, these weights tell us how important data points are, these data points are. So, like, let's say this is best to do as an example. Let's say we're classifying, once again, because that's easy. We're classifying movies. So we're trying to say, is this movie a positive, or was this movie a positive, a good movie, or a bad movie, right? And so what we could do is take every single frame of the movie, right? Okay, this doesn't make much sense, but we could take every single frame of the movie and so that's our sample, one frame. And then we can input into our neuron every single RGB pixel value, like the RGB pixel value for every single one of those frames. And then our model, Okay, this is better not to say if a movie's good or not, to say if it's a cat or a dog. So our model will take every single one of those pixels, all right, and then it will try to assign an importance to every single one of those pixels. So what it'll do is it'll take every single one of those pixels and say this one is important, this one isn't important, this one is giving me some sort of line maybe, this one is giving me some sort of, I don't know, something else. That's what this neuron is doing. It's taking these inputs and it's creating a scalar and applying some sort of function on that. It's doing something to that. And now here's where it gets interesting. This new data point, this new scalar value, like let's say this is equal to like b, well this we said it was equal to a, right? So this is equal to a. Well now guess what? I just take that value and then feed it into the next layer. And so each of these layers just gets one of these a's as their data point, right? So this first layer takes the original unfiltered data. This second layer takes the filtered transformed data from number one. So every single one of these neurons are receiving some sort of output from these guys' functions. And so each of these just do the same thing. They just take their input, which is from the first layer, and then they apply some sort of function on it, and then they just pass that to the last guy. And then the last guy takes every single one of those values and says, okay, well in the past I saw that a 1101 equals a dog, and a 1001 equals a cat, and usually when the values are higher then it's a dog, and when the values are lower it's a cat. So if I get a 0000 then it's probably a cat. So I can say with a 98% confidence that it's a cat. And that's how the thing works. Like it's not too hard, right? This, how it outputs this is called something with an activation function. We're not going to go that much into detail. It uses a specific one called sigmoid. Doesn't matter either. But like this is it. This is how it works. Isn't this cool? So everything else is just updating the weights, right? How do I make the weights better? How do I make these inputs, like how do I make these neurons have something, give something meaningful? What these represent graphically, that's a very difficult question to answer. Especially when you have something like 512 neurons in one layer and you have like 10 layers, right? Well then it's almost impossible to tell. But this is how it works. This is how deep learning works. So that's pretty fucking cool.